So now we will see how we can compute the distribution of cell network with the performance of cell network with multiple antennas. So I'll explain the channel model for this. We assume that each base station has M antennas and number of users served is psi. And here for simplicity, we assume zero force beamforming. So if you use different multiple antenna techniques, the analysis would change. So I will just have taken one particular multiple antenna technique, which is zero force beamforming, right? And if psi is equal to 1, this just means that I am beamforming to a single user. And then if psi equal to m, this means I am doing a full dimensional spatial dimension multiple access where I'm trying to serve all m users using m antennas. Okay, so there will be m streams, one stream for each user. And psi equal to 1 means there will be only one stream, right? But because I'm using all dimension to beamform, I would get better sign. So now the interesting point here is that interfering and serving links have different distribution, right? So in the past, when we have seen that we generally used to assume that both the serving and the interfering have Rayleigh distribution, okay? Or even if you take different like Nargami distribution, we kind of assume that they are subject to the same environment, so they have same distribution. Okay, here that is not the case because there is some precoding you do, right? According to the user you are serving. So the serving link is inherently different than the interfering link. Okay, so when you are serving, then you do some precoding based on your user. Okay, but the interfering if you are interfering, you do not do anything according to that. That is just like a side effect. You are interfering, that's unintentional. So you don't do anything there, and because of that, the distribution is different. Okay, so here you see one user. It has two base stations. One is located at X1, one is located at X2. There is serving base station. It does some precoding for this user. So some beamforming. So the polar distribution is H1. And if it's an interfering one, it is serving some other user. So it is precoding for the other user. And unintentionally, it is also interfering with this user. So its distribution is known as G2. And the distribution is basically different. Okay. And we can show that if base station at X is the serving base station, receive power is given as receive power is transmit power into distance to power minus alpha into HI, where HI is a random fading coefficient with distribution gamma delta comma 1. Right. This is specific to the zero force beamforming. So here delta is equal to m minus psi plus 1. So m is the number of antennas, psi is the number of user you are serving plus 1. Okay. And if the base station at xi is the interfering base station, the receive power is given as. So then the receive power is given as PIP into xi minus alpha to gi. Here gi is a random fading coefficient with distribution psi comma. Okay. So you can see serving and interfering have different distributions. So this actually have a lot of impact on the association strategy. Let us first assume the instantaneous association. Let us compare two base stations at xi and xj. If xi is selected, the SINR from that base station would be this. And if xj is selected, the SINR would be this. Now you can notice that jg and hj have different distributions, and hi and gi have different distributions. So you cannot create a coupling argument between them, and therefore you cannot say that the union of SINR I more than tau, even if for tau greater than 1, is same as if I sum over all this. Okay, it may happen that both of them, right? If suppose HI distribution and HG distribution is very high, but JG and JI distributions are very low. So in this case, it's possible that both SNR I and SNR J is more than tau. Okay, but there will be only one of them which is bigger. So this will be only one, but this will give you value 2. So that creates some problem that you cannot apply this law there. However, union bound can still be applied. This means if you recall union bound, the probability of union of some events is less than or equal to summation of probability of the individual events. Okay, and this is unity when these events are mutually exclusive. So this will give you an upper bound, right? And if I apply that, and if I write expectation that SNR I more than tau, then I can further solve it because SNR tau is Px minus alpha h upon I plus noise greater than tau. Okay, and this will give you the similar expression that h is more than this, and then you solve first for h, and then you solve for the interference. Now there is a problem that earlier h, the fading we have taken as the exponential. So this just gives a nice exponential minus tau p minus alpha x alpha. But here it is gamma distribution. Okay, so gamma distribution of integer value d parameter, probability that h is more than tau is given by summation from n equal to 0 to d minus 1 upon n factorial t n x minus t. Okay, so if you apply it here, if you look at here, this is h into some coefficient into I. Okay, I have neglected noise for now, but you can just add noise also. That is not going to change the approach. So this is just s into I. So what I wanted to compute is probability h is more than si. Okay, so if I is deterministic, then this will just mean that I will just put, instead of t, I will put si. So this will give me 1 upon n factorial si to power n exponential minus si. But if I is also a random variable, I have to compute its expectation with respect to I. And then when I compute, this will be just e in exponential minus si. Okay, so when the d was, when this was exponential random variable, then you, which means this say gamma d is 1, right? So gamma 1 comma 1 is same as the exponential distribution. Then you will not have a term of in, you will only have exponential minus si. So expectation will be Laplace, which we computed. Right? But here, this is not just Laplace. You have to compute the expectation of en into exponential minus si. Okay, how do we compute that? So we notice a nice trick that if, so we all know Laplace is given as this following format. If I differentiate with respect to s on both sides, and you can take the differentiation inside expectation. So this will become e to the minus si. If I differentiate with respect to s, you get minus I into e to the minus s. Similarly, if you double differentiate, you get I square into the minus. So if you do a n-time differentiation, what you get is 1 minus n power n in e minus si to exponential. Okay, so this is what you want. Right? This is what we want to compute. So the key is we need to differentiate the Laplace transform n times to get this. Okay, so this I can write in the following format. This is same as saying d minus 1 from h0. Sn is outside, Sn upon n factorial, and this is the nth derivative of the Laplace transform. So I can compute the Laplace transform, then I can differentiate it n times, and then I can apply here to get the coverage probability. Okay, so here and s value is this one, so I have to put the value of s also this. Okay, so Laplace transform can be computed easily. Right, you can try it. You will see you can apply the trick and take the random fading outside. So there will be only this exponential d to the power alpha term. Okay. Now the trick part is how do we compute derivative of Laplace transform? Okay. So because Laplace transform, you will see this will be exponential of some integration of S, right? So this is a composition of two functions. So to compute this, you may use Faddy-Bruno lemma. So basically, you can refer my memo paper to get more to how do we apply Faddy-Bruno to solve it further. Okay, here I want to cover a more interesting fact, which is known as the stochastic ordering. And this can help you to compare two scenarios without even computing them completely. Okay, so let us see what is stochastic ordering. Consider two random variable x and y. X is set to stochastically dominate y. I write it as x stochastically dominate y. So this looks like x is bigger than y, but this is not bigger than, this is like x stochastically dominates y. Right? X and y are random variable. So, bigger is not a valid concept. What you want to say is x stochastically dominates y if the CCDF of x is always bigger than CCDF of y for all values of x. Okay, so if I plot the CCDF of x and y, the x CCDF should be above CCDF of y. Okay, and if this is the truth, then you can prove that expectation of x is more than expectation of y. Okay, because if this is a positive random variable, you can integrate CCDF to get the expected value. Okay, so if this term is more than that, the integration is also more than that. Okay, so here you can also look at these two distributions, and you can basically get that this value always takes, for the same it has higher probability. So this has a bigger expectation. You can also show that if f is an increasing function, then fx is bigger than fy. So how does this help us? Right? So let us see for one if you stochastic ordering results first. If x is a gamma random variable with parameter m, and y is a gamma random variable with parameter n, right? You can assume that the rate parameter is 1. Just I'm talking about the shape parameter. So x as a shape m and y as a shape n, and both are gamma random variable. Then if m is more than n, then you can say that x stochastically dominates y. Okay, so this gives us an interesting result that if x1 is gamma m1 and y1 is gamma n1, x2 is gamma m2 and y2 is gamma n2, and if m1 is more than m2 and n2 is more than n1, then x1 upon y1 stochastically dominates x2 by y2. So let us compare two MIMO schemes, one with Psi1 users, another with Psi2 users, using stochastic ordering, right? We can see that schemes with lower number of users gives higher assignment. Okay, so you can basically show using this one. Right? You can just write the assignment expression using these two MIMO schemes, assuming that the base station is using the server Psi1 users or Psi2 users, and then you just put down the value of the interfering and serving base stations, and you will conclude this result. Okay, all base stations are using basically Psi1 users or Psi2 users. So both the interfering and the serving distribution will change. Right? Now I can also show that if x is more than y, then 1 upon x, sorry, x stochastic dominates y, then 1 upon y stochastic dominates 1 upon x. So how do we show that? This means probability that x is more than s is more than or equal to probability y more than s for every value of s, right? So instead of s, I can also put 1 upon u, that the result would be still true, right? And this is same as saying the probability that 1 upon x is less than u. This is saying probability of probability of 1 upon y less than u. Okay, so this also means that 1 minus probability of 1 by x more than u should be more than 1 minus p of 1 upon u y more than u for all value of u. Okay, so this means that probability of 1 upon x more than u is less than or equal to probability of 1 upon y u. Right? So this just means that 1 upon u y stochastically dominates 1 upon x. So this can also help us in comparing, in selecting base station. Let us take the average assigner base association, and let us take single antenna case. Feeding is exponential random variable in that case, and let us compare two base stations x1, xi and xj, and we want to see which one we should select. So if xi is selected, assigner I would be probability of si minus alpha hi upon p into xj minus alpha hj plus rest of the interference, and assigner j would be similar, but the serving interference terms will be interchanged. Right now, hi and hj's, even this hi and this hi are different copies, right? But from coupling argument, you can show that there would be one realization of fadings where you will get the same hi because they have the same distribution. So how do we select between the two, right? Now we know that if x and y are random variables with mean 1, then ax stochastically dominates by if a is more than b. Right? This is a very simple exercise you can do. If you multiply x and y are both exponential random variable, if you multiply x by a higher number, you would get a random variable which stochastically dominates the rest. So if xi is norm is less than xj, means xi is the closest base station, then xi minus alpha is less than, sorry, xi minus alpha is more than xj minus alpha. Okay, so this means p into xi minus alpha to hi stochastically dominates p xij minus alpha h. Okay, similarly, you can also show that 1 upon this xj minus alpha hj also stochastically dominates p over x minus alpha. Okay, now if you multiply them both, you get assigner I. So you can also show that assigner I stochastically dominates assigner j. Okay, so which implies that expected value of assigner I is more than expected value of assigner, right? So if I select xi base station, the closed base station, I'll get a assigner which stochastically dominate the assigner which we have gotten if I selected the second base station. Okay, not the closed one, the exit. So this means that selecting the closest base station also gives a scenario where your assigner is also maximized. Okay, and this will also maximize your expected assigner. So the average receive power maximizing association is also the average assigner maximizing association. Okay, so if someone asks you what is the strategy you will use if you want to maximize the average assigner, you will just select the closest base station. Okay, but when you have multiple antennas, things would be different because then hi and hj have different distribution. So you have to see if you can find some stochastic dominant conditions, right? Which is still possible, but for it, only few set of parameters of number of users and number of antennas. In this class, we will learn about how to model and analyze heterogeneous networks. So a generally heterogeneous network or HETNet have multiple classes of base stations. So in the past, we have seen that all the base stations are similar in network in terms of transmit power or number of antennas. But practical scenarios have cases where you have different types of base station all coexisting in a network. Right? For example, you can have millimeter wave network and in along with a cellular network, and users can also deploy. So they suppose they take an example. There is a macro cell. There is a macro base station which is installed by a cellular operator, and then there are pico cells which are also deployed by the cell network. which to optimize, yes, so to increase this coverage. But the power of the picocell is generally smaller than the macrocell, and it is basically to use to cover particular coverage holes. And then users can also deploy femtocells in their house or in their office buildings to further enhance the coverage. And its transmit power is further different than the rest of the base station. So such kind of network is known as heterogeneous network because there are different types of base stations. So, and then there can be multiple macro base stations because it's in fantastic, making a complete network. So a headnet is basically has k different tier, and each of these class is known as tiers, and they may have different parameters. Means they can have different transmit power, different number of fitting, or different density. The kth tier has power pk, and it's modeled using a point process 5k with density lambda k. So each 5k is given by a set of points xki, where xki denote the ith base station of the kth tier. So the complete set of base station can be seen as a superposition of all those 5Ks, and we generally use them to be independent of each other. So the combined base station process will also be a PP with the combined density. So in that case, the total density of the base station will be given by the summation of all those tiers. And if the user is free to choose the closest base station or any the best base station from any tier, then suppose it chooses the ith base station of kth tier, then an assigner is given by the transmit power of the kth tier, which is a serving base station, multiplied by the path loss interfering, divided by interference over all tiers and all base stations of these tiers except the serving base station, and then there is a noise also. So now you can see that if there are suppose tier 1 macro station and tier 2 femtostel, and these are denoted by blue base station, denoted by red base station, the superposition will also be PPP. Okay. But if you want to still distinguish between them, we can basically assign marks to these base stations. Right? We can say that there is a mark red or a mark blue. Red denotes this is a complete base station which denotes complete point process, or the point process denotes the set of base station. But each base station has a mark. If it is red, then it is a macro base station. If it is a blue, then it's a femto base station. But the whole thing is a point process with density lambda 1 plus lambda 2. Okay, so you can also see that similarly you can say that if I have a superposition of the base station, if I don't have any marks, then they just look like a set of base station. But if I have mark, then I can distinguish between the two tiers from this. So if I randomly assign marks, right, I will also get a PPP. So suppose the density is lambda 1 plus lambda 2. So if I assign red color with lambda 1 upon lambda 1 plus lambda 2 probability, and blue color with lambda 2 upon lambda 1 plus lambda 2 probability, I will also get to a union of two different base stations. And the first one would be the probability of the density would be lambda 1 plus lambda 2 into lambda 1 upon lambda 1 plus lambda 2, which is lambda 1. The second base will be lambda 2. Right. So the exercise just tells you that even if we have two different point processes, we can see them as a combined point process with a mark. And whenever we want to get back those point process, we just thin the point process based on the mark. So if I have this superposition, I want to get the set of base stations which are macro. I'll just thin this using the mark. Suppose I say m equal to 1 means it's a macro base station, m equal to 2 means it's a femto base station, then I can just choose all the base station which is m equal to 1. So how do I compute the coverage probability? If we assume the instantaneous assigner-based association, then this result is still true that for tau greater than 1, the union over all assigner over all TS and all base station is same as if I sum over all the base stations of assigner. The assigner gives tau. Okay. Now what I want to you look at here, I go to each tier and I go to each base station of the tier and ask if your assigner provided by you is more than tau or not. Right. I want to apply a trick here. What I want to do here is I want, instead of 5k, I want to sum this over all 5, right? But just to make the summation still equal, I will multiply by an indicator that xji should belong to 5k. Okay, so for each tier k, I am summing over all 5, but since I am already multiplying that, xji should belongs to 5k only. This means this summation will only be over 5k. Okay, so these two are same. It's just a different way to write this, and the reason I want to write this way, it will be evident in very soon. But I want to apply use Campbell-Mackay theorem, but for that you need to have the summation over the complete file. Right. So this I want to converge probabilities, and this will be probability of this one or the expectation of this one. So if I take the expectation of this TS and there is summation over KTS. So expectation is linear. So I can take expectation inside. So this will be summation over all TA, and the expectation over all points of the all base station in the point process. Of the indicator that assigner provided them by them is more than tau and multiplied by that base station belongs to K3. Okay, and let us denote this particular object as PCK tau, which just says that whether a base station which is of K tier can provide, at least one of them provide assigner more than tau. Okay, so this is this particular summation is the probability that at least one base station of all tiers provide assigner more than tau. This piece, which I denote by PCK, just tells the probability that at least one base station of the kth tier provides more than tau coverage. Okay, so now you can see that if I put the assigner expression here, this will become this way, and then you can see the assigner is a function of phi and phi minus phi minus xji, and this is a function of xji's. So this is nothing but summation of function of xgi comma phi minus xgi. Right, so I can apply Campbell theorem here to get lambda integration of and because the PPP again, instead of the palm expectation, I can use a regular expectation because it's the next theorem. So I get expectation of indicator that assign RGI more than tau, but indicator as belongs to 5k dx. Okay. Now this probability and this probability are independent, right? So I can break this expectation inside these two terms. So if I look at this one, expectation of indicator x belongs to 5k is same as probability x belongs to 5k. Right. Now x, we know that x is one of the points of point process, and the probability that it belongs to k tier is given by lambda k upon lambda. Okay. This is just the you can prove because 5k is the probability density lambda k, and rest total density is lambda. So the probability that the base station is k tier is just proportion to its density. And this term would be probability that is more than tau, right? I can again apply if h is a Rayleigh fading, if I assume Rayleigh fading, h is exponential random variable, so this will give me exponential minus tau I plus n divided by pk norm x minus alpha. Same as the previous case, I can break them into noise and the Laplace interference. So right, and this lambda cancels, so I get 2 pi lambda k integration of this noise term, Laplace interference evaluated at this value x dx. Okay, so then it is similar to that. Remaining is to complete the Laplace transform of the interference, and here note that at any user, the interference will come from all the base stations of all tiers if they are the same frequency. So, and then because I've assumed that all tiers are independent, the Laplace interference is summation of all those items. So I is given by I1, which is the interference from first tier, plus I2 interference from the second tier, plus up to In, or sorry, Ik. So the Laplace transform of I would be given by product of Laplace transform interference of individual interferences. Okay, and individual interference Laplace I we know how to compute. So you have to just take the project of that, and then you will get a complete Laplace transform. And if I put it there, and then remember the coverage probability is summation over all coverage probability of all tiers. So there will be summation here. So this is the coverage expression you will get for the head networks. Okay, this is for the instantaneous assignment based association. Now let's move to the average power based association. Right? So you remember when we talk about a single tier, it's the same type of base station, and we discussed a average power base association. We saw that, which is nothing but the closest base station association. We saw that the complete area is divided into small coverage areas. Uh, and in terms of closest, if I assume closest base station base association, the coverage region of different base station can be given by the Wernicke tesselation of the space. Okay, so you have multiple points. You compute the Wernicke tesselation of these points, and each coverage of each point will be given by the Wernicke set of that point. Okay, in the case of multiple tiers, you get because each base station have different transmit power. The average power base station, if you remember, the average power is a multiplication of transmit power into path loss, which is gamma x to minus alpha. Right. So this is not just distance bit, but it is also weighted by the transmit power. Right? So if some base station has a very huge transmit power, its coverage area will be naturally bigger. Right. So you can think that if there are two base stations, and one base station has 1000 watt and the other base station has 1 watt of power, and every user, even if it is more close to the second base station, the average power from the first base station can be more because it has a very high transmit power. So in that case, we get a Wernicke tesselation, but we get a weighted Wernicke tesselation where the weighing is done by the transmit power. And it would look like something similar to these pictures. So these bigger macro Wernicke cells are nothing but the macro tier cells. And this small coverage area are the coverage area of this Wernicke cells. Sorry, the small cells. Okay, and they are generally, take a very nice convex uh, this thing, and they don't like Wernicke. So they look like drops in the Wernicke set of microcells. Okay, so these are known as the weighted Wernicke cells. So you can see that if we take head nets, and depending on what parameter is different, you will get different types of Wernicke cell distributions. Now we will talk about in brief some other modeling techniques, right? So we have covered a basic system analysis for downlink, cellular, and uplink. We have also seen how we can extend it for heterogeneous networks, multiple antennas, right? And then there are other different scenarios which requires little bit change. So we will learn how these modifications can be taken care by stochastic geometry models. So first would be how do we include frequency reuse? Right? Normally, you know that if in a conventional model you have these nice hexagonal cells, and to avoid interference, we sometimes use different frequencies in the conjugated bands. So I divide the spectrum into three parts: red, green, and blue. These are three different spectrums, and I assign some base stations as red, some as green, some as blue spectrum. So here, if you see here, they will, this green and blue spectrum uses base station will not interfere here. The interference will only come from the transmitter operating at the same frequency, which are this, and this. So because of the higher distance, the interference may reduce. Right? So this may improve your assigner little bit. In stochastic geometry model, which is a random model, you don't have these nice patterns. Right? So instead of coding this way, what we can do is randomly assign different spectrum to these base stations. So as you can see that you can randomly assume model this single scenario by randomly assigning different frequency bands to these points. Right? So I have you can do by using marks. So you take each point, assign a mark out of 1 to 3 randomly. Whatever is 1, you will assign to this red spectrum. All the points with mark 2, you assign to this green spectrum, and somebody with mark 3 assigned to the blue spectrum. So this way, basically, you can cover all those. You can model the frequency used in a wireless network, and then if you look at this, if you want to take a user. And you want to compute its coverage, then you can notice that all the base stations which are in the same frequency, only those will interfere. So you have to thin the interfering network with a with that retaining probability, right? So if you are equally assigning all the spectrums, then the density of the interfering base station would be 1 by 3 lambda. Right? So the Laplace of the interference will change. Sampling distribution will still be same because you will choose whatever is the closest base station. Now let us see how do we model analog beamforming. So in the MIMO case we discussed, we have used a zero forcing, which was kind of a digital beamforming. You collect all those coefficient and then you do digital processing. Right? Many times when you go to higher frequency, you do not have those many RF chains. So you do not have capability to do digital beamforming. In that case, you just do analog beamforming, and this is the case with the millimeter wave. So in analog beamforming, you can think of it like a lens, right? That you cannot you can steer the lens into different directions. Think about a light ray coming, and then there's a lens in front of it. By steering the lens in a different direction, you can rotate, you can focus the beams into different directions. Right? Similar is with the millimeter wave case. You have a antenna, and by steering it mechanically or electrically, you can focus beams into different directions. Right? But it's analog beamforming, so you cannot, you don't have a capability to have different streams beamformed to different directions. Okay. Right, you cannot even have like different frequencies bands being formed in different directions. So analog beamforming. So the way it is executed is you have a phase shift array and like an array of multiple antennas, and then you change the phase of each antennas, and depending on the phase shift, you will have beams into different directions. So that's done in the analog domain. So basically, what happens is using different phase state angle, you get a particular pattern of the antenna, right? So this may look like you have in some direction you have some high gain, in some direction you have different gain. So this gain will be a function of the angle, right? So the receive power will be given by the transmit power into fading into into H is the fading, R into minus alpha is the path loss, and G is the antenna gain, which will depend on the angle, user orientation actually, right? So we can model this, a simple model to model this pattern would be this sectorized model, where in this angle of theta B, you would have a gain of G1, and the rest angles you have gain G2. So if this is your base station antenna or any antenna, and then you want to calculate, there is a user here, and you want to calculate calculate the gain at this user from this base station. So you will make a line, right? And you will calculate the gain in this direction. So if the angle is less than this angle, then the gain would be G1. And if there is a user here where the angle is more than this one, the gain would be G2. Okay, so if there is an interfering base station, and so if it is serving base station, you can assume that the serving base station always orients its antenna. So this is a user antenna orientation. So it can always orient its angle to the user. So the gain will always be given as the serving base station. But for the interfering base station, look at this. This is the interfering base station. This is the user you want to compute the interference at. And this interfering base station has own user, right? Suppose this is own user. So it will align its antenna pattern to antenna orientation to this user, right? So you can think that there will be a pattern at different thetas from this interfering base station. So if I want to compute the typical UE antenna gain, I will take this theta. I will put the antenna gain here and compute what will be the antenna gain in this direction. Okay, and again, if you assume the UEs are stationary, located in all direction, you can think that this theta is a uniform random variable between 0 to 2 pi. Okay, so this makes it a bit clear. If you antenna is oriented this way, the beam pattern can be modeled using this sectorized pattern. So in this angle, the gain is theta b. This side gain is given. In this angle, the gain is 0 2. And in this particular case, typical u is outside this gain, so the gain would be g2. Okay, if the typical user was here, the gain would be g1. Okay, so what is the probability that so instead of exactly calculating this one, we can again use a simplified approach. We can think that this typical UE can be the UE of this interfering distance can be uniformly around it. So this orientation angle can be uniformly around 0 to 2 pi. This means this theta, right, will also be uniform random between 0 to 2 pi, right? So this will get a gain G1 if this angle falls in this range, which is minus theta b2 plus theta b. Okay, so if theta is between minus theta b by 2 to plus theta b by 2, then we call the link is aligned and the gain would be G1, right? And if you assume theta to be uniform random variable, probability of this would be theta b by 2 pi. Similarly, in otherwise scenarios, the gain would be G2 and the probability of being unaligned would be 1 minus theta b upon 2 pi. Third, we will see how do we model partial buffers. So normally we assume that the base stations are always loaded. It means there are users in each base station looking for data to receive, right? But this is not always the case. Sometimes some base station may be idle because there are maybe users in the base station, but none of them is basically wants to receive any data, right? Or sometimes the user may move out of the coverage area. Suppose consider a very dense network. The base station is very close by, so it may happen that some base station does not have any user in there. So, and also, so model this, and this is crucial because if there is no user, the base station may shut down. Right? So, so this is known as a partial buffers because some base station may not have users to transmit. The way we can model them is, so if you have each base station and each base station has a queue of users, okay? So you can see some base station have a large queue, means these many users want to receive data and the base station would serve them one by one. Some have a small queue and some have a queue empty. Okay, and this is very true for even high data rate networks such as millimeter networks. They are expected to be very burst, so they will not have full buffer. So in that case, you have to model the partial load, and then you have to switch off the base station which does not have a user, right? And this is important because this will reduce the interference at other base stations. Okay, and this is also very important when you talk about densification. Suppose you want to increase the base station density. If you keep on increasing the base station density, the interference also increases. But beyond a point, you will see that most of the base station does not have a user, so they can be shut down. So that way the interference will reduce. So how do I model this thing? Right. So in reality, modeling this would be a little bit difficult, but there is a very simple model which people use. What they do is they compute a distribution of users in each cell, and then they compute the probability that a base station does not have any user. Let's call it P0. Right? So whenever the base station does not have a zero probability, a zero user, sorry, it does not have any user, this base station will be shut down. So the inactivity or the idle probability of the base station is also the same, P0. Right? Now, these P0 are dependent actually, but instead of having them dependent, we can model them by independent thing. So I take each base station and thin them based on a probability P0. Right. So I only retain base station with probability 1 minus P0. So I get a base station density with lambda into 1 minus P0. Okay. So now the question would be, how do we compute the distribution of number of users, right? So this is very interesting result. This is again empirically calculated. Uh, you can compute the number of users associated with an arbitrary base station and with probability, right? Which is given by this. So number of users associated with an arbitrary base station with is and with probability this one. Okay, where U is the ratio of the user density divided by the base station density. This is the basically average load per base station. Okay, and this is different than the distribution of user associated with the serving base station, which is the tagged base station. Okay. Uh, so we have shown that in the given the formula for that in the rate coverage probability. What is the distribution of users in the tag base station? But this is for a typical base station. This is the user distribution. So probability that the base station is off if nu is 0. So probability that nu is 0 can be computed by just putting n equal to 0 here, which is given by this. So the active base station density will be given by lambda into 1 minus P0, which is given by this. So we model that the new base station process, the active base station, is a PPP with this density. Okay, and because from this we will compute the interference. Okay, there will not be any change in the serving base station distribution because there the idleness does not come. Right, you have a user, you find the closed base station, and then that base station has to be on because there is a user associated. Right, on the rest of the base station, you have to see whether they have a user or not, and then you will turn them on. The fourth modeling technique we can do is to compute the mean association over TS.